We reconvene on Topic 11, Effects and Threats of Nuclear Radiation, and we welcome from Berlin Professor Geraldine Thomas from the Imperial College London. Thank you very much for joining us, Professor.
Pleasure.
Professor Geraldine Thomas is a Professor of Molecular Pathology at Imperial College London. She received her degree in pharmacology from the University of Bath in 1982 and completed a PhD at the University of Wales College of Medicine in 1988. Professor Thomas established the Chernobyl Tissue Bank, which will come to in evidence, which provides infrastructural support for thyroid cancer diagnosis and research into the molecular mechanisms that underpin the increases in thyroid cancer seen after the Chernobyl accident. She's published extensively on the molecular pathology of thyroid cancer and is author of a number of reviews of the health effects of radiation exposure following nuclear accidents. She was invited to speak at expert meetings on the health effects of radiation held in Fukushima in September 2011, and was invited by the UK Chief Scientist's Office to join the UK-Japan Dialogue on Nuclear Energy in 2012. And the Commission calls Professor Geraldine Thomas.
Professor, if I might start, who do you consider what are the credible sources of information concerning the radiation effects from both Chernobyl and Fukushima, and perhaps you might want to deal with them separately?
Yeah, I think there's major organisations like UNSCEAR and WHO, and when they set up reports, they get people literally from around the world who are experts in their field to give their opinions. I've served on some of their committees, and it's very much your opinion. You're not expected to toe a party line. And we draw all of the evidence from the scientific media, so from journals and things like that. And you have to remember when you read scientific journals that not all journals are equal. There are some that are much more reputable, therefore much more difficult. They require scientists to put an awful lot more input and facts and consider the options when they're writing the papers in their discussions. So those are the places that we really go for scientific results. We look at the scientific design, are there enough controls and things like that. So it's quite a detailed dissection of what's been put in the scientific publications by a number of people with different disciplines. So you get an all-round approach to the subject. So I would say probably UNSCEAR and WHO are the major sources of the real scientific effort that's gone into this.
It's been put to us that those organisations are populated with pro-nuclear individuals. Clearly, you have a different perspective.
I don't think that's true. I think, unfortunately, that the problem that you have is, I'll be quite honest, I was anti-nuclear until I started working on Chernobyl, and I was forced to look at the results coming out of the Chernobyl studies and actually say, this is not what we really thought. Everybody thought we were going to see far more cancers and things like that arising from Chernobyl, and you have to start questioning where you get that information from, and were you right to have thought that way? So I would say actually it's likely that most of the people around those tables started off as being broadly anti-nuclear, but they've had to look at the scientific facts and say our assumptions weren't right, our hypotheses are right, and that's what a scientist does. You have a hypothesis, you look at the facts, and then you question the hypothesis again and say, does that hypothesis fit the facts? And if it doesn't, you have to change your viewpoint. So I would not say that they were predominantly pro-nuclear or anti-nuclear. They're just scientists doing their job.
All right, we might unpick some of that then.
Can I just ask, in terms of your involvement and participation in the constitution of those sorts of committees and special projects undertaken by UNSCEAR, were they constituted of people that also included people with medical science experience and knowledge?
Yeah, you get a broad range of physicists, people who are experts in medical radiation and things like that. So a really broad field of people.
And in terms of the information gathering, in terms of the data collection, did you also interact with people that had medical science or particular medical qualifications within hospitals or other institutions?
Oh, absolutely. You have to remember, actually, the doses that come from medical radiation are quite a lot higher than the environmental doses. And often you'll find doctors are even more cautious than the environmental-based scientists, simply because they've been taught all the way through their careers that, radiation is quite dangerous and you have to be careful how you use it. So, yes, there were epidemiologists, but there were also medical doctors on those panels.
Right. Perhaps if we can just come to some just very basic fundamentals, and we'll hopefully move through this quite quickly. I'm just interested to understand whether or not there are particular radioisotopes that we need to be particularly alert to. We've heard much about cesium and iodine with respect to their consequences for human health.
Yeah, isotopes are different. You know, you can't sort of use a broad brush and describe them. The effects on health really depend on whether they have a long physical half-life and depend on whether they're taken up into the body and bound so can release the radiation while they're inside your body. What you have to remember is we tend to think our bodies stay the same the whole time. They don't. We're continually losing stuff from it and taking stuff in. That's why we eat. And so the balance of the biological half-life, i.e. how long that particular dose of isotope you've taken in stays in your body before it's replaced by the more widely available stable isotopes, because all of these things exist as stable and the radioactive isotope stays. So the actual health effect depends on the balance between the biological effect and the physical half-life. So to use iodine and cesium as an example, iodine 131, which is the one that we talk about in terms of health effect from Chernobyl, for example, has a short half-life of about 8 days, physical half-life. But your thyroid needs iodine to make its hormones. If you don't make thyroid hormones, you have all sorts of problems with brain function, and it generally controls the whole of your metabolism. So that hormone is very important. Iodine is normally very scarce in the environment. So the thyroid over our evolution has developed a way of taking up the iodine into the thyroid and binding it to make the hormones. Now that means that its dwell time in your body is much longer than it would be if it just went in and came out again. So because it's got a short physical half-life and a long biological half-life of about 100 days in most people, that means it's got a chance to release all of its radiation while it's inside you. Whereas cesium, it's the opposite way around. Cesium doesn't concentrate in any particular tissue. There's no mechanism that we have that makes cesium stay particularly long in any of our tissues in our body. And it has a long physical half-life of about 30 years and a relatively short physical half-life of about 70 days. So it comes in and goes out and very little radiation is released. So the dose from cesium is an awful lot less than the dose from iodine. So it's a complicated thing, which is not surprising why a lot of people find it really difficult to get their heads around, because you have to understand the physics, the chemistry and the biology. So it makes it really difficult.
The Commission's also heard something about strontium. I know we've concentrated on iodine and cesium. Could you address strontium in the same way that you've just addressed those last two?
Yeah, the other thing to remember is things that are different weights. So you have heavy heavy elements like strontium, and you have the volatile isotopes like iodine and cesium. Because they're volatile, when you have an accident, they get thrown into the atmosphere and they'll drift around on the air circulation around the planet. Whereas things like strontium, because they're quite heavy, actually don't go very far from the site at which they're released. So you do get some strontium release if you look at the atomic bombs, for example, because these were above ground tests. They would disperse, strontium was dispersed a bit more than it would have been if that explosion had occurred on the ground, because it's a much heavier thing than the cesium and the iodine. So it does depend on the weight of the isotopes, their atomic mass, as to where they're likely to end up and whether they're volatile or as in strontium's case, not volatile that much. So you will get a small amount of strontium, but it is a relatively much smaller amount of strontium from something like a nuclear plant having a problem. And the other thing is we do tend to equate atomic bombs with nuclear power plants, and they're not the same things at all. They release different things, and the kinetics of how those are released into the environment is very, very different, because it depends on whether it's an above-ground explosion or whether it's an explosion based on the ground, as to where those things get distributed.
I'll come back to those differences later, because I think we might work our way through each of the three different, the Hiroshima and Nagasaki circumstances of Fukushima and Chernobyl. But I just wanted to come to another fundamental, and that is the issue of background radiation. And I just wonder whether you could give us some insight into your views as to the averages or the average ordinary exposure that humans receive to radiation. I think we might have a slide that picks this up. Do you have that available to you?
Yeah, I mean, it varies around the world, so it really depends on which country and even which region you're in. A lot of the background comes from radon that seeps up from the ground. So places like Cornwall, for example, in the UK, have much more granite, and Edinburgh have much more granite and therefore have a slightly higher radon dose. So that affects the sort of the background radiation that you have. And there are areas of the world like the coast in Kerala, which has thorium in the sand, where they have a much higher dose of background radiation because the rocks are quite different. So it's the geology that really affects the background radiation. And also in places in America, actually, it's much higher. It's 6 millisieverts compared with 2, around about 2 in the UK. So it does vary, and also different societies obviously use medical radiation differently. So that has a slight effect on the dose. So if you're in somewhere that doesn't use CT scanning, of course, your dose is going to be slightly lower on average than somewhere else where they use an awful lot of medical interventions and things like that. So there are lots of things that affect the background dose. And some of us will get more dose than other people because some of us fly a lot. Every time I go to Tokyo on the return flight, I get 0.14 millisieverts of radiation from cosmic radiation. So your habit as a human also can affect that. And of course, there's radiation in food. Things like potassium-40. Bananas are a really good source of potassium, very good for you, but also contain a bit more radiation than other things because they have a lot of potassium-40 in them, because they take that up from the soil as the plants are growing.
Just coming to the chart, that's the pie chart that's there, for which particular population group is that? Is that the UK?
That's the UK, yeah. But I mean, that's actually fairly average for most people. So, you know, in some areas of the world, you might get a bit more radon from background rocks, but in most places, that's about average. That's probably about the same in Australia as well.
Yeah, I think we've just seen a chart from Australia that shows a greater proportion for artificial sources, about 1.7 millisieverts for CT and medical uses. So I think it's a little bit more than 50%.
Yeah, I mean, it might well be that, you know, in Australia you're going to use that an awful lot more than you can say in the middle of Africa, for example.
Yes. Now, I just wanted to deal with the issue of LNT. We've received in the submissions significant amounts of information about views about the LNT hypothesis or assumption, and I'm wondering perhaps first of all whether you could offer some insight into that particular discussion or debate and where there's consensus or not consensus with respect to that issue.
Yeah, LNT is a good example of, as a scientist, you should never have a hypothesis that you can't really test. And that's the problem we have with the LNT. We've got lots of information about radiation effects at high doses. The trouble is, as we've just been talking about, we're all exposed to radiation. So if on average I said that there was an average dose of 2 millisieverts, which is probably a bit on the low side per year for each human life year spent on the planet, and you die at 70, you're exposed to 140 millisieverts over your lifetime. So when you get down to the really low doses, you have a problem in being able to design the study to decide what is due to the radiation, because you have that background effect. And so when you get below about 100 millisieverts, we know the effect is very small. There's quite a steep slope on that line. We know the effect is very, very small, and it becomes incredibly difficult to actually show an effect because of all the other things that affect our health.
Yeah,
if you like, you look in the noise. It's like looking for the needle in the haystack when you get down to those low levels to define what is due to the radiation and not due to everything else that affects our lives, which of course is complicated because over a lifetime, how we live changes markedly. I mean, we didn't have the internet and things when I was a young child, and everything changes in life. So your eating habits, all the other chemical carcinogens you're exposed to. So trying to define over a lifetime the effect of a very low dose of radiation, it gets lost in everything else that affects our health. And that's why there's so much argument about the lower dose range. We don't have many studies in that area because we can't do the studies. We don't routinely expose people to a little bit extra radiation, so it's quite difficult to get that data. And it's just a sort of a noisy area when you're looking at it to define things statistically, and that's our issue with it. So some people believe that if you have a little dose of radiation, it will actually pep up your DNA repair, which is what keeps our bodies going through our lives.
Is that the so-called homeotic view, or?
It's a homeosis.
Yep.
Yes, hormesis.
Yep.
So, I mean, a lot of people like sitting in spas, for example. Interestingly, the German and Japanese are probably the two countries that really go in for spa treatment. You're actually exposing yourself to a little bit more radiation in those places, and people think it's healthy. They don't think about the radiation, they just think it's healthy. But some people have taken that and think, well, a bit of radiation does you good. Whereas other people believe that we're far more sensitive to low doses of radiation. I think that's more difficult to say that's correct, because if a little bit of radiation was even more dangerous, we'd be seeing so many more effects from things like the atomic bomb exposure and the atomic bomb testing that we did in the 1960s, where the doses around the world got literally spread most. I think they didn't quite reach Australia, but they were virtually over the northern hemisphere, where we had actually quite a bit more radiation around in the atmosphere than what we would be used to normally from backgrounds. But we don't see huge increases of cancer. The increase in cancer we see is because we're living too long. So people are getting cancer as a natural thing of aging, which we can't really stop.
I'm just interested in your view as to the appropriate uses that can be put to the linear threshold. We've heard some evidence that it's appropriate to place store in it for the purposes of radiation protection. Is that your view?
I find it really difficult because, again, we will never ever have the evidence to say we shouldn't do it. So as a scientist, you tend to err on the side of caution and say, well, if I can't find the evidence, I have to assume the hypothesis was correct. I think we're actually getting to a stage now where all the other things that affect our health, are becoming more important than very low doses of radiation. So to give you an example, there's a good piece of work done by the Beer 7 report, which tries to put some of this into context. So they've used American statistics, and the Americans do have an awful lot of data on health outcomes in something called the SEER database. So they're a good source of good, hard scientific data. And they reckon that if you exposed 100 Americans, given all of the normal health patterns that we would see in America, to 100 millisievert, so that low level at which we start to have problems defining what the effect is, one of those would get cancer due to the exposure at 100 millisievert, but 42 others will get cancers from other causes. Now, to me, that really put it into sort of context and says, well, actually, I'm a bit more worried about the other 42 cases than the one case in the radiation at that level. And you can never remove all risk from life. It's impossible. So when you start making one risk really decide things where it pales into insignificance compared with the other risks, I think we have a problem getting our heads around what's safe and unsafe when you get to that sort of level. And we could be making other things more risky by trying to protect ourselves from radiation at low levels, for example. And you see that in the psychological effects of Chernobyl and Fukushima. We're too worried about the radiation, and it starts to actually have health effects. The worry has health effects rather than the radiation itself.
I'm just interested.
Does that make sense?
I'm just interested in understanding, with respect to LNT, its utility in reaching conclusions about the causation of radiation-induced cancer. And that is, I'm just interested in your view as to whether it's appropriate to multiply these predictions from very low doses by large population cohorts to predict outcomes.
Absolutely not. That does not help at all. To give you another way of trying to look at that, it's a bit like saying that as a man you wet shave, and if you cut yourself, you're going to lose a small amount of blood, okay? So if lots of men wet shave and lose a small amount of blood, if you add the blood up, that means somebody is going to die from blood loss. That doesn't make sense. That doesn't help you protect men from cutting themselves shaving at all, to suggest that it's so dangerous that if you multiply it up by the number of people who wet shave, somebody somewhere is going to die because they've lost so much blood.
Perhaps we can move away from LNT, and I think we can we've got a slide that I think picks up some of the discussion we've just had in terms of the relationship between dose and effect, and I think this is headed dose and effect. Do you have that in front of you?
No, I don't. Hang on a second. The table I sent you, yeah?
Yes. Yep.
Yes. Yeah,
So
I know that table backwards.
I think we've dealt with we've talked very low and low dose. Are you able to speak to the issues of moderate dose and high dose, just so we can round out dealing with that table?
Sure. So at moderate doses, you're getting to the area where you mean the sort of upper half of the table, yeah?
Yes.
So at moderate doses, you're getting to the levels of more than 100 millisieverts. So you're likely to see an effect in a very small number of people, but you will see the effect statistically in epidemiological studies. And at high dose, you're actually getting to the areas where you start to see direct tissue effects. So if you expose somebody to high doses of radiation for cancer treatment, for example, often the skin will go red, they'll start to feel sick, and those are what we call sort of the direct effects of radiation, where you actually get tissue injury. Now, you only need to expose a very small number of people to those high doses to see those direct effects. When you come down the dose range and you get to the medium dose levels, you're then starting to see fewer people affected. So to get a statistical answer, you need to expose many more people, but you will see an effect at those doses.
Yep.
But the populations need to be significantly larger than at the very high dose.
Yeah, we've seen similar information today expressed in terms of effective dose, in terms of millisieverts. And I noticed that this particular table is expressed in terms of absorbed dose, or grays.
Yeah.
And I'm just wondering what the relevant translation is here, just so that we're clear on that.
It depends on the type of radiation. So things like an alpha particle are a bit like a juggernaut running into your DNA. It's a very heavy helium nucleus, so it's physically going to do an awful lot more damage. So we apply weighting factors for alpha radiation. So it isn't a direct translation, but for most beta radiation it is a direct translation. So you can translate grays into millisieverts. And this is part of the problem that we have with radiation. It's complicated, it's not a straightforward thing. It's not like taking a chemical that you can say this dose causes this effect. You have to take into account the type of radiation that's involved as well. So to be correct, when you talk about doses to tissue, you should give the figures in grey. But it's much easier when you're looking at different types of radiation, and most of us are exposed to multiple different types of radiation. So in order to sum those individual doses together, you have to take account of those weighting effects. So we tend to refer to it as sieverts to give us one figure.
Now, just to pick up on some evidence that was given this morning, I just don't know whether are you aware of a statement to the effect, and I hope I've got this right, that about 30% of cancers are produced from natural background radiation, and that about the further 70% are produced from anthropogenic causes. Are you aware of any such statement to that effect within the medical or scientific literature?
Yeah, it's basically very difficult to be certain. Again, you've got the problem of so many things, cause and effect, that like cancer, that it's actually very difficult to tease out which effect is causing what percentage of cases. And, you know, it depends on the study you read, what people will say, but it's very difficult to get hard scientific facts. I would suspect actually smoking and obesity, sitting here as somebody who should not be the size she is probably far more deleterious to your health than exposure to background radiation. Now, you can't avoid that exposure, but you can avoid doing some other things that we know are much more dangerous to health, like smoking and being overweight.
Now, early in your evidence, we began to refer to some of the distinctions in the kinds of radiation exposure you got in particular events, and I indicated that we'd come back and deal with each of the particular significant population radiation exposure events in sequence. I'm happy to first come to the circumstances of the atomic bombs that were detonated over Hiroshima and Nagasaki, and I'm just interested, and perhaps we'll deal with sources as well as we go, but I'm just interested first of all to understand what's the consensus of scientific evidence about what the radiation-related effects associated with the Hiroshima and Nagasaki detonations.
Yeah, there's no doubt about it. The higher the dose, the more likely you are to have had cancer as a result of exposure. People tend to think that there was an awful lot of people affected by radiation. Yes, there was, but actually most of the deaths that occurred, and there were about 140,000 casualties in those two atomic bombings, short-term casualties. About 120,000 of that was actually caused by blast injury. I mean, this was a massive heat release, and that basically caused blasts, and it caused a heat surge which killed the majority of the population. About 20,000 of the people who survived that and lived in the very, very centre of the explosion died subsequently within a few months from radiation poisoning, which is the top end of that table I showed you. So those are the very high doses that give you direct tissue effects.
So this was a acute radiation sickness, as I understand it's called?
Yeah, so you see the effect immediately. And if people have had radiotherapy, they'll know that, a large dose of radiation that we use to cure many cancers, which is targeted to the cancer, does cause some systemic effects as well. So that gives you an idea of what that really is. But then you come down to the people who did not die from the immediate effects, but were exposed to fairly large doses, around about they give it in weighted colon dose, is the way it's referred to by the Radiation Effects Research Foundation. So some of them had large doses, 4 gray, 3 gray, and then you start coming down into the milligray. And most of the population that survived those explosions had lower end doses, okay? So there was quite a lot of low dose exposure, but it was exposure to gamma radiation predominantly, not to the particulate radiation like iodine 131. There was some, but not as much from cesium. So it was mainly gamma ray exposure. So it's quite different from a scenario as an accident in a nuclear plant, for example. And there is a clear dose response in that the high doses result in more cancers. The low doses, there's a slight inflection of the curve at the bottom, suggesting that the low doses are not quite as bad, if according to the LNT, as you might expect. But it's actually very difficult, because once you get down to that 100 millisieverts level, you're looking at a very small increase in cancer over the background rate. I mean, they did very large studies. They did 86,000 people were in the studies that they looked at, and they followed them over their lifetime. So many of those people are now in their 70s and 80s. And we know there's an effect on, if you were much younger at exposure, the effect is likely to be greater. So you're more sensitive to the lower doses than if you're an older person, for example.
Yeah, I was going to come to the sources of the information upon which you've relied for the answers that you've just given in terms of effects. You referred to a number of 86,000 people studied. What's the source of that study, and what's the nature of that study?
That's the lifespan study, and that was a very big cohort study that was set up as quickly as they could, given the effects of war in that area, to look at the effects long term on the population that was exposed. That runs from the Radiation Effects Research Foundation in Japan, and it is a very major undertaking to follow that number of people throughout their lifetime. And it's a good source of well-collected data that's been collected in a regimented fashion, so you know that the data is not changing over time because of the way we're looking at the data, for example, and collecting that data. So those sort of studies need to be set up from the word go, and set up very strictly to make sure that you don't introduce bias into them. So it's a well-conducted scientific study with appropriate controls.
And has that study itself been the subject of peer review and analysis?
Oh God, yes. You don't get any of that published without it going through peer review. And people will tear papers apart. So, it's peer review is not an easy process. People tend to think it is, but real peer review and the journals that sort of information is published in are really rigorous journals. That's been subject to great peer review. I know there's a lot of people who think that it's not being conducted properly. But I'm afraid it is pretty rigorous in the way it's being conducted, and those are the facts, and I'm sorry, but that's what the facts are.
Now, you drew a distinction in your evidence earlier between the nature of the radiation exposure from an atomic weapons detonation and the consequences of a nuclear power plant accident. I'm wondering whether you might expand on what you see as the key distinctions.
Yeah, I mean, for a start off, the atomic bombs are exploded above ground, okay? So the atmospheric conditions are quite different, and the way that the material is distributed is quite different. What is released is quite different. Yes, you do get cesium and iodine released as well, but for example, the iodine will stay up in the atmosphere for longer before it comes down to the ground in rain. So because it's got a short half-life, there's going to be less of it than what was actually released by the time it hits the ground, and we get exposed to it. It's interesting actually that people tend to think that if sorry, the pop-up just came up on my screen then. People tend to think that, what's the train of thought? Sorry, I'll go back.
We're drawing a distinction between what follows from atomic weapons testing and from nuclear power plants.
Yeah, people tend to think that there's been more exposure from the nuclear power plant accidents, but if you actually look at the figures for what was released in the atomic bomb tests, not the bombs themselves, but the tests that carried on in the 1960s in America and Kazakhstan and places like that, we actually released far more cesium and iodine into our atmospheres and strontium as a result of those tests.
I think we've got a slide. I think we've got a slide that picks that up, and it contains a table.
And I was quite surprised when I saw that.
And it would be helpful, I think, to the Commission if you might unpack the information that's contained there. It uses a particular, as I understand, it's a petabecquerel. And I'm just wondering whether you can explain what a petabecquerel is.
A becquerel is a measure of radioactivity, so it's the amount of radiation, it's the radioactivity that's released. And a petabecquerel is 10 to the 15 becquerels. An individual becquerel is very, very small, the disintegration per second. So you're looking at very, very large releases, and in actual fact, it was nearly tenfold that came from these above ground tests in the 1960s, compared with something like Chernobyl. So it was 85, I think it is, petabecquerels from Chernobyl, and it was nearly 10 times that much from the above ground tests. So we worry about the nuclear accidents, but actually far more was released in the 1960s. And there's a lovely graph that you can still get the data, the original raw data from one of the DEFRA websites. Is you can actually plot the amount of strontium and cesium in milk in the UK from the above ground tests. And in the 1960s, that was substantially higher than from the Chernobyl accident. There was virtually no strontium in our milk from the Chernobyl accident in the 1980s, but you could see cesium in that. So it's interesting, we tend to forget about the above ground tests and concentrate on the two nuclear accidents. But actually more radiation was released from those tests than either of the two nuclear accidents that we've had more recently.
Now, again, I understand that this is drawn from the source of this information is one of the UNSCEAR reports, is that right?
Yeah, there's two reports. There's the UNSCEAR report from Chernobyl, which references that table, and then the Fukushima data comes from the later Fukushima report. They're all public documents, so it's perfectly, anybody can access these online if they want to. Now,
I'm just interested, perhaps at that point, if we can come to the particular circumstances of the Chernobyl accident, and I'm just wondering whether there's anything particular about the circumstances of that incident that has had a particular consequence in terms of the release of the radiation from that particular accident that distinguishes it from Fukushima.
Yeah, I mean, the power plant was quite a different design, and now when we build nuclear power plants, we always put a containment facility around the core, which means if there's something happens to the core and there's a release of radiation, there's another shield, or like a firewall around your computer. There's another shield so that you don't get released straight into the atmosphere. It gives you time to do things like move the population away, or get them to close their windows and doors and things like that. So it gives you a bit more time to deal with the situation and keeps that radiation inside the plant rather than releasing it to the atmosphere. Chernobyl didn't have that. The power station there was what they believe happened was this was an incident where they were doing a safety demonstration. They were trying an experiment with the reactor, I've been told, and I think it's probably true, that the train from Moscow, because you have to remember this was Soviet Russia at the time, was late, and there was a crew that went off duty who'd been trained how to do this particular procedure, and a naive crew came on. And you didn't do those things in Soviet days without the people from Moscow coming to watch you. And it was basically human error that caused the accident. And what happened was they removed the rod that would normally moderate the reactor, but the safety features were disabled. It went out of control. They couldn't do anything to save it, and there was a massive steam explosion, not a nuclear explosion, and people confused the two. This was a steam explosion, which basically blew the roof off the building and ejected part of the core. It was a very big explosion. But in Fukushima, it was very, very different. I know the whole world saw an explosion, but actually that was the outer containment breaching. That wasn't the reactor core going up. So the amount that was released in the two accidents are very different because the core was exposed following Chernobyl, so much, much more was released at the Chernobyl accident than was released in Fukushima because all the safety systems kicked in Fukushima. Whether there weren't any safety systems working at Chernobyl, they turned them off to do the experiment.
So I'm just interested to understand, with respect to the exposure of the core at Chernobyl, did that have a particular consequence in terms of the radioisotopes to which Soviet Russia and the remainder of Europe were exposed?
Yeah, I mean, the problem when a nuclear power plant explodes is you get releases of volatile isotopes. Things like strontium, because they're heavier, don't get ejected as far, so they stay in the vicinity of the reactor. So when you have an explosion like that, the iodine and the cesium go up into the atmosphere and get driven around on the circulation of the winds, and that's exactly what we saw. If you map where that contamination went, you can tell which way the winds were blowing. So originally the winds went north. There was also a fire in the reactor as well, and that burned for 7 days. So it took them 7 days to extinguish that, which is the pictures that some of us remember of seeing helicopters flying over and dropping things down, was trying to turn that fire off. But that took about 7 days. So for 7 days, it was leaking radiation into the atmosphere. So it was quite different from the scenario at Fukushima, where it was under control fairly quickly. There it burned for some time. It carried on releasing radiation. And in fact, we didn't know anything about it in Europe. And because we didn't have all the fancy satellites and things that we have now, we didn't know anything until an alarm went off at a power station in Sweden. And the Swedes thought they had a release and got really worried. But in actual fact, that was the air travelling across, carrying the radiation from Soviet Russia, and it hit the detectors at the Swedish power station. And that was the first inkling we had that something was wrong. And that was a week later, so it took a whole week for that cloud to pass across Soviet Russia and hit the Swedish border. And of course, during that week, half of the radiation from the iodine will have gone because its physical half-life was so short. So it was pretty obvious we were detecting something that was a major release in that area of Russia. If the wind had been going the other way, we may never have known about it, because of course the wind would have taken it right the way across to the east and over Russian territory.
Now, I'm just interested to understand, we'll come in a minute, I think, I want to address what you understand the key health effects have been following the exposure at Chernobyl.
Yeah.
But I'm just interested in understanding about the evidence collection and to the extent to which there was evidence collection associated with effects on human health and what's been undertaken in terms of those studies.
There were a number of large studies set up fairly quickly. The Japanese actually were the first to really respond with that, and they set up large-scale screening. They literally sent vans that were able to screen children to Russia and went around the local communities. So there was a lot of evidence gathering within that. That was probably in the early 90s. I mean, you have to remember that when it happened in 1986, it really was Soviet Russia. It was not easy to get into that country, but there were people who were allowed in fairly soon after the accident. So you had some people from the EU, for example, were allowed in to see what was happening, to gather some evidence, and actually to put together packages to actually help recovery. So from the very early times, there were people evidence gathering in there, but the real major studies of the effects on health, because we know the effects on health are going to be slightly longer term, didn't really get going until the early 90s, but the Japanese, the Sasakawa Foundation, started running large screening programs. The Americans started putting a lot of money into cohorts, similar to the lifespan cohort, but really intended not to be probably as long as the lifespan cohort. But those are still ongoing. They're still obtaining data. And what they do there is they collect people who've got thyroid cancer, who've had a diagnosis of thyroid cancer, and pair them up with people who had a similar exposure and live in a similar area, and then follow them through the rest of their life to see what the effects are. So it would have been nicer to have had much more data. Not many people had direct thyroid measurements, for example, but there were some, and not many people undertook detailed questionnaires. And it's important to know what people were doing with the inside of the thyroid accident, what food they were eating. Were they eating lots of milk-containing food, for example, which we know gets more heavily contaminated from the iodine fallout. So it would have been nice to have more data, but actually we've got quite a lot of data that tells us the doses that individual people have. And if you're going to relate cause and effect, you need those doses. So there is a lot of data, and it's well-constructed studies that have been conducted into protocols that most scientists would accept are the best that we could do at the time.
Now, I think you've indicated that there were a number of studies, and I'm just interested to understand we're aware that there was a major report produced by UNSCEAR. This is in the decade after the 90s, so this is, as I understand, a major report released in 2008. I'm just interested to understand, are you aware of the sort of...
There was one report from about 2000 as well, so there's been two major UNSCEAR reports. The most recent one was 2008, which actually wasn't released publicly until 2011, just before Fukushima. But 2000 was the first report. And that really... we were still actually getting data at that point. So that was a sort of preliminary report, and with the 2008 we've got far more data, so we've been able to assess the health consequences much, much better with the longer period of follow-up.
Yeah. Did those reports include information concerning these medical data sets from these cohort studies? Did it consider those studies?
Yeah, they were starting to give early results at that stage, so yes, they were included. More importantly was understanding the doses and the amounts of release and trying to get that right, because actually you're reconstructing doses because people weren't physically there measuring things at the time. So that was important to get right as well. But yes, you were starting to see certainly some of the cases of thyroid cancer. We were definite there was a problem in 1992. There was no two ways about it. This was not detection due to screening. This was definitely a rise in childhood thyroid cancer, and only childhood thyroid cancer. So you had about 8 years worth of data from those screening studies into that first report in 2000. But obviously you had more in 2008.
And I know this may seem obvious, but did that involve people that were medically trained?
Oh yeah, absolutely, absolutely. I mean, that was one of the reasons that I got interested in this. My boss at the time was probably the foremost thyroid pathologist, and he and a gentleman who's now sadly dead, an Italian endocrinologist, both went out in 1992 and actually sat in clinics with the medics in Belarus, seeing these patients as they came into the door. So no, these were, people who were really at the top of their game, experts in their field, who went out to conduct these studies.
Okay. Now, I just want to turn... We mentioned in introducing you the concept of the Chernobyl Tissue Bank, and I'm just wondering whether you might explain what the Chernobyl Tissue Bank is and what its purpose is.
Yeah, it became fairly obvious, in about the mid-1990s, that the people in Ukraine and Belarus were very keen to understand what was happening. They wanted to be involved in a lot of the science, and they had a tendency to be giving researchers material from the same patients, which means when you come to do the meta-analysis, you're actually looking at the same patients and you don't know it. So we thought a better way of helping them to do this, and a better way of giving research scientists good material to work on, was to actually develop a tissue bank where we collated all of the information about the pathology and about the types of tumours that were coming, and collected biological specimens so we could try and understand whether there was something different about the way radiation induces cancer, or are we looking actually at the same cancers but just more of them? Because if there's something different about the way the cancer is being developed, we might need to change the way we treated people. So it was really to try and understand how radiation affects the molecular biology and how it induces these cancers. But it was to do it in a programmed way so that all researchers around the world could get access to this material, so the best science could be done on the material, to make sure it was collected ethically, because the rules in Ukraine and Belarus are not quite, at the time, they've strengthened things, but at the time were not quite what we would have accepted in the West. So it was to encourage them to do this in a proper way, in a standardised way, and in a way that we could follow over time. A bit like setting up the cohort studies, but this time with tissue, because we wanted to know what radiation actually does to the tissue which causes these cancers.
Yeah. Did that involve cancers other than thyroid cancers?
There weren't any. That was the problem. I mean, people keep thinking we're going to find other cancers other than thyroid cancer. There has been no increase in any other cancer in the populations at large. I'm not talking about the cohorts of liquidators now, I'm talking about the population at large. There has been no other increase in any form of cancer other than thyroid cancer, and there's a really good reason for that. The reason is there was an awful lot of iodine released. This is the first time we've ever exposed 10 million children to iodine. We don't see effects on the adult population, we only see it on the children. So this increase in thyroid cancer is restricted to only those who were young children at the time of the accident. And the reason for that is that it's A, they probably drank more milk than their parents, so their dose was higher because the milk was contaminated. But also the thyroid in a child continues to grow. It has to reach adult size. And that added growth increases the ability for the cells to become cancerous. So it was important that we collected that, and of course it's a particularly sensitive group when you deal with children. It's sensitive whichever country you're in. And people expected there to be other cancers. I thought there might be breast cancer, for example, because the breast has an iodine pump, but it doesn't keep the iodine within the tissue. So it takes it up, especially when you're lactating, but then it releases it again very quickly. So the actual dose to the tissue is much smaller than it would be for the thyroid, where it takes it up, hangs on to it, and it releases its iodine while it's inside. And it really brought it home to me when I actually saw the figures from the epidemiologists about doses from cesium. Now the cesium, some of it was skimmed, they took the soil off and disposed of it, but a lot of it stayed on the ground, and that map that we were talking about at the beginning shows you where that cesium deposition was. And of course you grow crops in cesium. This is a rural economy where people grow their own food and they eat their own food. So people were exposed to cesium, and I was expecting to see something from that because that's the way we'd always thought about radiation. Low doses would be very, very dangerous. But when you work out how much the dose is to people, just carrying on their normal lives, eating the crops they grow in the garden, over 20 years, about 6 million people got the equivalent of 9 millisieverts each, okay? That's the equivalent of one CT scan, whole body CT scan, for example.
Now, can I just...
Because cesium's long-lived physically, short-lived biologically, the dosage is much, much lower than you would expect. So all of a sudden you start to realise, well, hang on, that's why we don't see any other cancers, because the two principal isotopes, the iodine, yes, does cause thyroid cancer, but the cesium dose that you get from it is so small that we just don't see the cancers, because we wouldn't be able to pick them out from the noise of the other things that cause cancer in that particular area.
Yep. Can I just go back through that answer? And I'm just interested in the question of sources of the information that we've just discussed. And that is, I think we started with a statement about there not being cancers other than the thyroid cancers.
Yeah.
In terms of what studies do you rely on to reach to express that particular conclusion?
Those are the large epidemiology studies that have been done. I mean, if you're looking for something that you want to look at the mechanism for how something is caused, first of all, you have to see that there is something causing it. So you can't do the studies on the molecular biology unless you can see an increase in that cancer and then look at the excess rate. So you can only study an increase in cancer if you do proper cohort epidemiological studies. And all the cohort studies have shown us that thyroid cancer is the only one that is increased. There is lots of noise in the scientific, not quite so reputable press that give you anecdotal things of, oh, somebody's got this cancer from that. But there's actually no studies that show that is the case. And you have to do this in a scientific way because cancer is caused by so many other things. So unless you do the right design studies, you're going to end up picking up cancer from other causes and think it's due to the radiation. You have to design these very carefully in order to find out exactly what is causing it.
Can I just come to the thyroid cancers? And you expressed a view about the increased risk, particularly with respect to children, but not in the adult population and their exposure.
Yeah.
Again, what are the studies, what's the sources, the information that you refer to with respect to those conclusions?
Again, it's the epidemiology studies. There has been less done in the adult population because thyroid cancer becomes so much more common in the older population. So you'd have to do massive studies in order to look at that. Childhood thyroid cancer is very, very rare. So you can see an increase very quickly. And this was a large increase, it's 100-fold increases in some places. As you move into adulthood, thyroid cancer becomes a lot more common, even though it's still a rare cancer in terms of cancer terms. But in order to see an increase with the population that you've got, you have to do very large studies. And because we knew children were more sensitive, we did concentrate more on the children. So because we knew that's what we could see, and of course you have to remember we have to get funding to do these studies as well. So you have to come up with a proper design that everybody is going to believe the result. Otherwise nobody's going to fund the study too. So there has been more concentration on the younger people because we knew they were much more at risk and we could define the population. The adult population has not been so well studied, but there have been some studies in that population as well, and we just can't see an increase. And the simple way to do this is just to plot cancer rate over time, and you can see that there's a cohort effect. So the youngest ones carry that risk with them. So there's no doubt about it, it is the youngest who are most at risk from this, with all the studies that have been done.
Now,
Professor, there's been evidence also this morning about genetic disease caused by the Chernobyl accident. Is there any evidence?
Absolutely none. You have to remember that to have genetic disease, you have to get a radiation dose to the germ cells. Your germ cells are pretty well protected. So to get a large dose to the germ cells is actually quite difficult. The studies that were carried out after the atomic bombs, where the doses were much larger and you would have expected to see much more effect, still have shown absolutely nothing in the next generation. So there's no generational effect at all from the atomic bombs because the doses, the individual doses, not the collective dose, which is a totally wrong way to look at it. The individual doses are so much lower. It would have been amazing to see that because you would then assume that anybody who had something like a CT scan that would affect their children in the future. And it just doesn't work scientifically to even suggest that at those doses. A lot of people did have abortions because they were scared, and we saw that after Fukushima as well. Some of the people were so scared that their children would be affected, they had abortions. But the doses, there was just no scientific evidence to suggest that they would be at risk. But people are scared and they do react in different ways. And it's very easy to blame something like radiation if you're looking for a reason why something isn't right in your life. And I've seen that with people I know should know better. It's still an automatic response to try and find something to blame if you have a problem with your health or your children's health. But there's no scientific evidence for it whatsoever.
so again, in your, coming back to again the answer from earlier, and you expressed I think a generalised statement or an average with respect to an average exposure in terms of about 9 millisieverts for the general population that was other than the localised emergency workers at Chernobyl. And I'm just interested to understand what's the basis for that estimate, how that was calculated, and where does one go to find that as a piece of material?
Yeah, that's using data from the map that we were discussing at the first, so we know what the local...
We'll pull that map up if we've got it. Oh, we don't. Sorry.
Yeah, but so that you'll know what the soil contamination is. You can take questionnaire data to work out how much people were eating during the time, and you can also use whole body scanning. They are doing that in Japan at the moment. People are being whole body scanned to look at the cesium burden they have, and in most cases they can't find any cesium at all in them. But there's a variety of different ways you can look at it, but most of them will use sort of environmental measurements and give you an estimation of the dose, because it's actually quite difficult to go and scan that number of people in an area like Belarus and Ukraine, and it's, so you can work out from all of that data what the estimated dose will be.
I just want to then come to the question of outcomes, and that is in terms of deaths and other reported illnesses. And perhaps we can deal first with the localised workers. That is, as a result of the Chernobyl accident, what's your view of the state of the evidence with respect to the number of people that were in fact killed by radiation exposure from the Chernobyl accident?
Yeah, I mean, there are 3 people who were killed as a result of the explosion, nothing to do with the radiation, just hit by flying debris and things like that. There are 28 firemen, and these are the guys who were hovering over the reactor core and were exposed to very large doses of radiation. 28 of those have died within a few months as the result of acute radiation sickness. There were a total of 134 people who actually had acute radiation sickness, so had very large doses, and 28 of those have died. 14 of them went on within, I think, about 5 years of the accident to have children who were perfectly okay. So even those who had high doses, their children were perfectly okay. There have been around about, again, you have to take into account of about lag time. So what was reported in the 2008 report from Unskir, from Unskir was 6,000 cases of thyroid cancer. They're going up by about a few hundred each year. Now, of those, we know of 19 have actually died from their disease. Okay, so these were people who unfortunately came to the clinics late and had metastatic disease, and we were unable to treat effectively. And over about 50 years, so up to about 2025, we would expect, based on the data that we have at the moment, to probably have about 16,000 thyroid cancer cases as a result of the radiation. Okay, so more than we would have from the normal incidence of thyroid cancer. Thyroid cancer is one of those things that we can cure very effectively, ironically by giving very high doses of radioiodine, because the thyroid cells take up the iodine and they get a large dose of radiation and that kills them. But even so, we would expect about 1% of the people who get thyroid cancer to eventually die of their disease, and that could be many years after they have their first primary cancer. So that would be about 160 deaths, for example. About 30% of them we would expect to come back with thyroid cancer deposits elsewhere in their body, but again, most of those we can treat very effectively with radioiodine. So if you sum all that up, you've got 28 people who definitely died from acute radiation syndrome, very high doses, their bone marrow packed up. You've got 160 predicted deaths, so that gives you something like just under 200. Now, you've got a little in a fudge factor, because until you have that complete data set, you will never know the exact figure. But, 200 to 300 probably maximum. The assumptions that are in a paper by Elizabeth Cardis, which reviewed all of this on the 20th anniversary of the accident, suggested there might be about 25,000 other cancers. But the evidence doesn't seem to say that that's necessarily going to be correct, because the doses to elsewhere in the body were so low because they come from cesium. We based that data on what we would predict if we used the models that we used for the atomic bombs on that population. That may not be the correct model to be using. So at the moment, there are estimates, but what we do know is about 19 of the children who have thyroid cancer have died from their thyroid cancer, and 28 workers have died from acute radiation syndrome. The others, who, although they had acute radiation syndrome, they had sort of lesser forms of it, are still alive and well, apart from a few who've died from smoking-related illnesses, alcoholism and car crashes, which you really can't put down to the radiation. Because, of course, as that population ages, they're going to die. We can't avoid death, unfortunately. Well, not yet. I don't think we really want to in the end. So, that population will die, but it won't necessarily die of anything to do with radiation.
You gave a number from an analysis that had been done. I think the surname was Cardis.
Elizabeth Cardis.
Yeah, of 25,000, was that 25,000 cancers or fatalities?
Cancers.
Cancers, right.
And interestingly, as we get better at treating cancer, of course, they may not result in death from cancer, because in medicine, if you cure somebody, it just means they die from something else. That's what a cure is.
I just wonder whether you based on your involvement in work, whether you think that there are any particular key lessons that have emerged from our understanding now of the Chernobyl accident in terms of the cancer risks.
Yeah, I think if you'd asked me when it happened, I think everybody was scared there was going to be lots of leukemia and different sorts of cancer. Now the evidence, and it is very good, hard evidence, and that's part of the reason I think people did not speak out, scientists particularly don't speak out without data. We don't like giving false information. So now we have the data and we can see that actually the major cancer was thyroid cancer, in fact the only cancer was thyroid cancer, which we would not have predicted from the beginning. But interesting, if you go back with hindsight and you look at the animal models predicted exactly that. It would be young children who would be most at risk, and they would get thyroid cancer and nothing else. Even when we treat with radioiodine, very high doses of radioiodine, that does get elsewhere in the body, because that's why we're giving it to patients to get rid of their thyroid cancer. You do find you get a small number of secondary malignancies as a result of that radiation exposure, but that's much higher levels. So my guess is that thyroid cancer will remain the only thing that we actually can prove was due to the radiation. It's very difficult to disprove that anything else went up because of all the other effects that give us cancer. And that's partly part of the scientific conundrum we find ourselves in. You can't disprove something, but you can prove it. And we can't disprove there was any other type of cancer if we're totally honest scientifically. But the chances are that the vast majority of all the other cancers in that population were not caused by the radiation at all. Were caused by alcohol, smoking, all the other common factors that we know about. But pinning the exact amount down to radiation in our population, as I've said before, at low doses, very difficult, and I would say almost impossible. But we keep trying to do it, and that's part of the reason that people are still worried about radiation, is we can't give them a definitive answer, if we're really brutally honest. But what I can say is I would be more worried about living with somebody who smoked than being exposed, even as a liquidator, in the lower dose category of liquidators, to the radiation from Chernobyl. Smoking is far more dangerous. And in fact, smoking also has radiation in it because it has polonium-210, which is an alpha emitter. So a smoker who smokes on average 1 pack of cigarettes a day over a year will get the same dose as if they had a CT scan.
That's additional.
That's additional.
Can I move to Fukushima? I think we've already dealt in part with the differences in causation, and I'm just interested in terms of the key isotopes we need to be concerned about in terms of emission from the Fukushima incident, and then move on to dealing with the health effects from that.
Yeah, I mean, it's the same two isotopes. It's iodine-131 and cesium-137, the longer-lived version of cesium. Those are the two isotopes that we're concerned about. Those are the ones that were released in highest quantities and got into the general population rather than just being in the reactor site itself. So those are the ones that are going to cause a health effect, if any, on the population.
Now, I'm just interested in, perhaps we can deal with, because we've dealt with iodine and thyroid cancer with respect to Chernobyl, you've got a view as to are there relevant differences with respect to the Fukushima incident?
Yeah, I mean, the doses at Fukushima were much, much lower, about 100-fold lower, even to those who were evacuated, and there are reasons for that. A, there was much less relief. B, the Japanese did exactly what they should have done, which was to move the population away. The Japanese don't drink much milk and things like that. It was cold, it was snowing, cows were inside, so they weren't eating contaminated grass for those people who do have milk in their diet. So there's lots of reasons why their iodine intake would be lower. Also, the Japanese eat a lot of iodine-containing seaweed and things like that. So your thyroid is a bit like a sponge. So if you put a dry sponge into water, it soaks up the water, and once it's got all the water contained in the sponge, it can't take up any more. And the thyroid's like that. So if you've got lots of stable iodine around, you're actually going to have all of your iodine binding sites in the thyroid will be taken up by stable iodine. So the radioactive ones don't go in. So there are lots of reasons why that doses were lower, but primarily there was an awful lot less released, and the Japanese authorities did the right things in terms of moving the population away and cutting the food chain. There's no doubt about it that the food chain and what you consume is the most important component of the dose. So you will inhale some iodine if you're standing outside, but cutting that food chain restricts the dose of iodine and cesium very, very effectively. And in Japan, they could do that because they can pull in food from other areas of Japan. Belarus, Ukraine, and Russia, because it's a rural economy, really couldn't do that. So, you know, if they said don't eat the food, if the people had actually done what they were told, and people notoriously don't do what they're told, you know, they'd have had a problem feeding the people who lived in that area as well. So the two accidents are quite different, both in terms of amount released and in terms of response by the authorities in the two different areas.
Yeah,
which is why the dose is so much different.
You expressed the exposure as being 100-fold less. Is that capable of being expressed in terms of either grays or millisieverts?
Millisievert. So it was the average exposure to evacuees from Pripyat was to the thyme was about 500 milligrays. Because it's a beta emitter, you can equate that to sieverts, so 500 millisieverts. The exposure to the thyroid from the people that were actually physically measured. There's no assumption in the dose. This was actually measured in the thyroid from Fukushima was about 4.2 milligray millisieverts. So we know the doses were that much lower. In the original reports that came out from the WHO, there were an awful lot of assumptions about how people would behave. So those assumptions went into the dose estimates. But it was interesting when they had dose estimates of about 80 millisieverts, for example. When they actually measured the doses were an awful lot lower because people had been moved away, they'd shut their windows and doors, they'd not eaten contaminated food. So it's pretty obvious that the measures were pretty effective in reducing the dose, which is the most important thing. No dose, no effect. It's that simple.
Yeah, I'm interested in understanding the extent to which there's been health monitoring of both the general population and those particularly in the Fukushima prefecture following the incident.
There's a huge study going on where they are monitoring the health of the population. That actually might not be helping the population, because if you're having your health monitored, you immediately think, I'm going to be ill, that's why they're looking at me, which actually psychologically doesn't help them that much. But there's a massive health survey that's going on, looking at different aspects. There's a big ultrasound study that's looking at the 360,000 children who were exposed, so under the age of 18. That is actually a survey, so all of these kids will be invited to participate in having their thyroid screened by ultrasound, which is an extremely sensitive technique, every 2 years until they're 20, and I think it then goes to every 5 years after that, just to monitor any effects on the thyroid. But there are also other studies looking at women's health, looking at pregnant women's health, looking at psychological effects as well. So there's massive amounts of data being gathered about that. And that's actually got a problem, because if you release that data without explaining where the data's come from, you can actually worry the population far more. So interpretation of that data for the public who aren't experts in whatever health field we're looking at actually requires quite a bit of skill and quite a bit of interpretation. Otherwise, you just get facts which don't mean anything to anybody.
I think we've referred to an analysis of cesium and iodine. Is there analysis of other particular radionuclides and their release and their health effects on the population?
There are huge amounts of people who are monitoring the environment around there, loads of studies being done. There's some people wandering around with cesium detectors just to see what the levels are on the ground, because you get very patchy fallout. And of course, if you're inside a house, you're not going to get contamination unless you walk through a contaminated patch and bring contamination in with you. So there's huge differences in exposure levels depending on where people are at the time and where it rained, for example. And also the soil that's involved. So there are lots of studies going on about that. But really and truly, we know that the isotopes that are going to cause the problem of the cesium and the iodine, because they're released into the environment, whereas most of the rest are very, very close to the power plant themselves. It's the volatile isotopes that cause the problem for general health. So there's massive amounts of data. that are coming out of those studies as well.
Are you aware, we've heard some evidence that suggested that there were some reports of illnesses consistent with some forms of radiation sickness following the Fukushima incident?
No, not true at all. I mean, you can feel sick for a number of reasons, and that's one of the first signs of radiation sickness, but it doesn't mean you've been exposed to radiation. The doses at the plant were very much lower than the doses at Chernobyl. Nobody got a dose of a sievert, which is the sort of borderline into acute radiation syndrome, at 1,000 millisievert. So the doses were much, much lower, even within the plant. And that's good. That's down to really good radiation protection and making sure that you monitor your workers effectively as well. And that was very important. And that's why so many people were involved, because they were changing the workforce to make sure that individuals' levels were kept as low as they possibly could, given the circumstances they were working in.
Yeah. We've also heard some evidence that suggested that there would be an epidemic of cancers that would be created as a result of the Fukushima accident. Do you have a view with respect to that?
Absolutely not. I mean, I worked on the recent IAEA report, and we went through every piece of evidence, and we were able to talk to the Japanese, really drill down into what was known, what was unknown, and the levels of radiation that came out of the plant and the doses to which the population was exposed. There will be absolutely no discernible risk in cancer increase. I have to say something though. There was a recent report about a gentleman who had leukemia who'd been working at the plant. The problem is the law is not our friend here. The law says that if you cannot disprove that it was due to an industrial cause, then you pay compensation. So because they were unable to prove that it wasn't due to the radiation, because we just can't do that, we can't prove a negative, he was given compensation. But I'm really worried about that, because if you look at the dose he had AML, which is reasonably common in his age group. If you look at the figures from what we have from the atomic bomb studies, actually 30 to 40-year-old, and this gentleman was, I think, 40, that section of the population is actually more resistant than younger people and older people to leukemia development from radiation. His dose was, I think, 15 millisievert or 19 millisievert, certainly under 20 millisievert. But his lifetime dose from other radiation sources throughout his life and background would have been 80 millisievert by the time he was 40. So to me, he's much more likely to have had leukemia from things other than radiation. And unfortunately, people in that age group do get AML, and that's a fact of life. I see people like that all the time in the hospital who've got AML around about that age group. Doesn't mean they're exposed to radiation. But unfortunately, as soon as you pay compensation, it becomes fixed in the public's mind and in the media's mind that it was caused by the radiation. That is something totally different. And there's certainly not enough evidence to say that. But unfortunately, that's the way the compensation laws work in terms of industrial exposure to things that might damage your health. And also, I should also say that smoking causes 17% of AML. And if you've been to Japan, the majority of Japanese men smoke.
Professor, thank you very much. It was very useful for us, and I thank you for spending some time with us on that evidence. We'll now adjourn.
Thank you very much. Thank you.